So this is from Lippman section 4.2. Quick little overview of what's going on here. And these are the big ideas that I'm hoping you're going to walk away from this section with. We're going to review, make sure you understand exponential growth and decay and long-run behavior again. Similar concepts, just applied to the exponential functions. What you need to remember from our earlier work is that the coefficient in front of the function is a vertical stretch or compression. Inside the parentheses is our left-right shift, and outside the parentheses is our up-down shift. And really, that's all you got to worry about is those three parts for exponentials. So now for this whole idea of exponential growth and decay. So when you have an exponential function, and maybe I should, so we looked at exponential functions last section, but remember, an exponential function will have a number raised to a variable, whereas a power function is a variable raised to a number. Okay, so we're going to be dealing with it with this. So we have exponential growth, and I'm sure you've seen that either in a math class or in a science class, where populations or money or whatever grow exponentially. And also quantities can decay exponentially. Radioactive isotopes, some of you might remember Chernobyl. They talked about how long it's going to be before people can safely travel around that area of Russia. So that's decay. So how can you tell the difference? Well, if you look at the base, anytime we have the base that's bigger than 1, that's going to be an exponential growth situation. So you got to be careful too, because sometimes you'll be given a function that looks like this, and you'll say, okay, the base is bigger than 1, that must be a growth equation. However, that exponent's negative, and if you think back to the work you did in college algebra or algebra 2, you can break that exponent up into that form, and when you have a negative exponent, that means you're going to take the reciprocal. That makes that 1/2 to the x power. Now you can see how that's a decay equation. So if your exponent's positive and your base is bigger than 1, you get a growth situation. If your exponent's negative and your base is bigger than 1, it'll be a decay. You can also, I just might do this to you. If I have 1/2 to the negative x, well, again, you got to take the reciprocal of that 1/2 and make it 2 to the x, a growth function in disguise. Okay, so now how do you match these up? Well, the faster the growth rate, the quicker it's going to grow. If you remember back in section 1 where they talked about 1 plus b to some t power, where the b is the growth factor, or growth rate, the growth factor is it together. So you can think about if this base is a bigger number, it means it's growing faster. So 2 to the x isn't going to grow as fast as 3 to the x, and 3 to the x is going to grow faster than e to the x. Remember, e is that number 2.71, it's a transcendental number like pi. Very interesting number. We'll use it a lot. So I'm looking at these. So let's figure out which ones of these C, D, E, or F matches up with these growth functions. Well, you see what's different about this one. I'm noticing there's a 3 times 2 e to the x. Well, if x is 0, 2 to the 0 is 1 times 3 is 3. So that tells me when I have a y-intercept of 0, 3. For these other 3 growth equations, 2 to the 0 is 1, 3 to the 0 is 1, e to the 0 is 1. So that kind of helps us decide that, see how this c function has a y-intercept of 3? Well, that's the same thing as the a, that leading coefficient, that stretch factor, whatever you want to call it. Okay, so that tells me c is this 3 times 2 to the x. Now for the other 3, they all go through the point 0, 1, and we kind of knew that looking at this. So now we just got to think about which one's growing faster. Well, this is a growth rate of, if you think about 1 plus b, that has a growth rate of 1 or 100%. This has a growth rate of 2, because 2 plus 1 is 3, so 200%. And this has a growth rate of what? 1 point, if you take away 1 from that, 1.71. So 2 to the x is growing slower than e to the x, which is growing slower than 3 to the x. So that tells me this f must be 2 to the x, e must be e to the x, and d must be 3 to the x. Okay? Now conversely, if you're looking at a decay equation, and these two are decay functions, because I know because the base is less than 1, this is, if you think about, go back to 1 plus b. Well, that would be 1 minus a half. This is going to be 1 minus 2/3. So the 2/3 function is going to grow, is decaying quicker, because that tells me it's losing. It's only a third of it remains, or 2/3. It loses 2/3 every time x increases by 1. That's only losing a half. So that tells me this is going to be 1 over 3 to the x, and this is going to be 1 over 2 to the x. And if you think about this, I mean, if I got 4/5 to the x, if I got 9/10 to the x, those are getting to be more and closer to 1. So the closer you get to 1, the less decay is going on. It's going to lose values slower. Okay, so I hope that helps with that. Now what we're going to be working with is transformations of exponential equations. The big idea is the graphs, writing an equation from the graph, but you also have to know how a function behaves. So we all have to check for whether there's any shift up or down. What's the Y-intercept? If you think back to the slide we just talked about, the A is going to basically be the, how does that come into be the Y-intercept? Not always, because if you have a C, that's going to change things a little bit. And then B is your base. Sometimes they'll tell us the base. Sometimes we'll have to figure it out, like you did in last section when you had to when you're given the 2 points. Okay, so I guess we can talk about long-run behavior. If I had y equals 2 times 3 to the x plus 4, that tells me I've got an exponential function that's been shifted up 4, it's been stretched 2, and the base is 3. It acts like 3 to the x, only it's been transformed. So if I think about this, normally exponential functions all happen to have a vertical asymptote, horizontal asymptote of the x-axis, and then they grow like this. They go through 0, 1. This one is going to have, because it's been shifted up 4, it's going to have a long-run behavior going to the left of y equals 4, and going to the right, it would go to infinity. So if I had to write that using that arrow notation, so as x approaches negative infinity, y approaches 4, and as x approaches positive infinity, y also approaches positive infinity, because these exponential functions grow. When they're growth equations, they head up to infinity. If it was a decay equation, let me go see if I can't do this with red up here. If this were a decay equation, I would say, I would kind of reverse these. I would say as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches that horizontal asymptote, that 4, that whatever this C number is. Okay, so hopefully that helps you, gets you a feel, do a couple of questions out of the book around that. Now we're getting to the meat of it. This says, they're telling us that these are transformations of y equals 2 to the x. So a couple things I'm seeing with number 29. These are out of the section in the book. Okay, I'm seeing a horizontal asymptote of 1. So that tells me it's going to be 2 raised to the x plus 1. Remember, that's that C number. If you think back to that other slide, we had y equals ab to the x plus c. Well, the c in this case is going to be 1. I know b is 2 because they told us that. Now, chances are, it's possible you'll have to worry about left-right shifts with an exponential graph. Not usually. I mean, Yeah, they come up, but I'm not going to stress it. I'm just more worried about you understanding, the long run behavior, recognizing exponential function, that kind of thing. So, since we know I'm telling you, I don't think there's a left-right shift here. We could test, but I'm not going to worry about it right now. The other thing I'm noticing is I got to worry about that A number. Well, I see that this has a Y-intercept of -3. So I don't know what A is. I mean, I could write -3, but I've got this darn 1 going on here. So what you want to think about is setting this up, substitute in your values. Well, y is -3 when x equals 0. So if I want to solve that for A, I'm going to get -3 equals A plus 1. So A has to be -4. So this function here will be -4 times 2 to the x plus 1. And you can graph that in Desmo or graphing calculator and check that out. Okay. Now this one, one thing you might want to pay attention to. This one was a reflected growth equation. This one, if you think about it, it's a reflected decay equation. So that might help you differentiate between exponential functions and log functions that we're going to do next. So I'm seeing 2 to the x function, but I know it's a decay equation, right? It's a reflected decay equation. So I'm going to just write this as 1/2 to the x. I could write 2 to the -x if I wanted to. Why don't I do that? 2 to the -x. Either one of these is fine. I know it's been shifted up 3. So I'm going to put a plus 3. And then I'm going to ask myself about that y-intercept. I'm seeing a y-intercept of 1. So I'm going to do the same kind of thing. I'm going to say 1 equals a times x to the 0. Or I could say here that this is going to be a, 1 equals a times 2 to the 0 plus 3. It's going to be the same kind of thing. So this case it'll be 1 equals a plus 3, and this will be 1 equals a plus 3. Same math, subtract 3, I'm going to get -2. So this function should be y equals -2 times 1/2 to the x power plus 3. And that kind of confirms what I was thinking. The leading coefficient's negative. That tells me it's reflected around the x-axis around this line, y equals 3. So we're good. I think that's it. So here's a graph they told us. They didn't tell us what the base was, so we're going to do a little bit of substituting in here. We know we're eventually going to have an equation, y equals ab to the x plus c. I'm seeing a horizontal asymptote of -4. So I'm thinking right now I'm going to write y equals ab to the x minus 4. Then I'm seeing a y-intercept of, 0, -1. But first off, we probably, well, does it matter? Let's find out what a is. So -1 equals a times b to the 0 minus 4. See, I didn't need to know what b was because b to the 0 is 1. So -1 equals a minus 4. A has to be equal to 3. And then I gotta find b. So what I look for here is a point that goes through a nice lattice point. I'm seeing that 1, 2. So I've got the point 1, 2. Let's substitute that into what we know. I know that 2 equals 3 times b to the first minus 4. So I'm going to add 4. That gives me 6. Divide by 3, that gives me b equals 2. Well, maybe somebody who's a little more with it than me would have noticed that. I didn't. So I think the equation for this graph is y equals, let's see, what was a? 3 times 2 to the x power minus 4. So let's see what we can do with this. Suppose we have to make a sketch of this graph without a calculator. So what are we going to see? Well, I'm seeing a y-intercept, a horizontal asymptote of -1. That tells me the graph's been shifted down 1. I see well, let's see, I know it's got some kind of reflection going on because that's negative. I also see this is going to be a decay equation because it's 3 to the negative x. So I could momentarily think of this as negative 2 times 1/3 to the x minus 1. So then I can think about this as, well, it's a decay equation that's been reflected around that line, y equals negative 1. And I also see a bit of a stretch going on. If I substitute in, to just give me a point of reference, let's figure out where this graph crosses the y-axis. Well, it crosses the y-axis where x equals 0. So that's 1. Negative 2 times 1 minus 1 is going to be negative 3. So this crosses, see, that was negative 1, negative 2, negative 3. I know it's a decay equation, so it's going to look something like this. And that's really a good enough sketch. That's all we need to know. We can see the concavity of it. We can, do a lot of things with it, and that's as exact as you need to be. So I hope that helps you complete the open math exercises. Go try some out of the book too.